Hi all, let's take a look at AP Review 1 in-class worksheet. AP Review 1 in class. This has some innocuous questions like what does f prime mean? Tell me everything. No, more than that, really, tell me everything. And there's lots of things we can say here about this. Um, perf. Okay. Lots of things that we can say about f prime. You know, we can say f prime equals y prime equals dy dx equals dy df. I'm sorry, df dx. Um, we can talk all about this notational stuff, but we can also say that this is the rate of change in f with respect to x. We know that f prime of x is the derivative of f of x, which means the slope at every point on f of x. So we could say, hey, don't forget you've got a limit definition derivative of this, the limit as h approaches 0 of f of x plus h minus f of x all over h. And that kind of brings up f prime at some point. This is the slope or derivative or rate of change at some point x equals a. And if we're talking about f prime of a, then we've got some limit definitions of the derivative for that, right? F prime of a equals the limit as h heads to 0 of f of a plus h minus f of a over h, or that alternative form that we learned with x approaches a of f of x minus f of a over x minus a. So there's a lot of things I feel like I can say about f prime. Can I say more about that? Oh, how about this? I can say that the integral of f prime of x is equal to f of x plus c. Don't forget we can go backwards as well. So f prime is kind of a big thing. The antiderivative of that is, the integral of that is our antiderivative. Let's take a look at 2. What's the first derivative test? What's it used for? Okay, so I make my f prime sign chart. I find when f prime equals 0 or undefined, and I plug those values on my f prime sign chart, and then I test these intervals, and I determine, aha, I can use this f prime sign chart to help me determine that there's a max at x equals a, because to the left of x equals a, f prime is greater than 0, and to the right of x equals a, f prime is less than 0. No sign change here. We go negative to negative, so neither a max nor a min at b, the way this sign chart looks. But if I have this, now I see that there's a min at x equals b, because to the left of x equals b, f prime is less than 0, and to the right of x equals b, f prime is greater than 0. So I can certainly use the first derivative test to help me find maxes and mins. Don't forget, we could also have maxes and mins at endpoints. From this point, my function is increasing, is what I learned from this. And so I know that there is a min at x equals c, because x equals c is the left end point, and to the right of x equals c, f prime is greater than 0. And here I can see that my function is increasing until we get to point D. And so I could say there is a max at x equals D because x equals D is the right endpoint, and to the left of x equals D, f prime is less than 0. Of course, if these changed, minus and minus, now I'd be talking about a different situation. From this point, I would be decreasing, so I would have a max here, and I would have to flip this. And here, my function would be decreasing until I got to point D. And so I would say I have a min at D, and I would have to flip this as well. So we get all that stuff about maxes and mins from our first derivative test, but we also get increasing and decreasing. F is increasing on A to B because f prime is greater than 0 on A to B, and f is decreasing on C to A union B to D because f prime is less than 0 on those intervals. Okay, so there's a bunch of stuff we get from the first derivative test. What does f double prime mean? Well, you know, when we were talking about f prime, I was thinking, well, couldn't we also talk about f prime greater than 0 tells me f is increasing? So now when we talk about f double prime, I want to think, well, f double prime, if y equals f of x, f double prime could be y double prime, could be the derivative of y prime, or f prime, right? We're going to take the derivative of f prime, and that's going to give us f double prime. So we could have that imperative verb form of the derivative, where we take the derivative of this to get that, as opposed to just the noun form, hey, this is the derivative of something. It's also the second derivative of y, or f in this case. We've got a bunch of different notation for that. Not only could we see y double prime, but we might see df dx, or dy dx. Take the derivative twice of y with respect to x both times. Okay, so we've got a lot of stuff regarding notation for the second derivative, but what does it mean? Well, it's the rate of change in y prime with respect to x. It's the rate of change in the rate of change in y, in y with respect to x. We could also say it's the slopes of y prime or f prime. We can say f double prime greater than 0 means f prime is increasing, and we also know that f would be concave up. And if f double prime is less than 0, that would mean f prime would be decreasing and f would be concave down. I really do need you to actually know these things, like, comfortably, especially this, going into the AP exam. Anything else we want to say about the second derivative? No. 4, second derivative test. Okay, so second derivative test. I have a f double prime sign chart. I've got a critical point at A. Remember, we set f double prime equal to 0 or undefined for our second derivative test. And then we test on either side, and we find, lo and behold, look, a sign change on f double prime, a sign change on f double prime at these points. And so we know that something is important happening on f at these points. We also know about f prime at these points. So let's say some of the things we know when we see this sign chart that we made by setting f double prime equal to 0 or undefined. Remember, here the second derivative test is usually used to find inflection points on f. But inflection points can't occur at endpoints, so unlike the first derivative test, where I'm going to check endpoints as well, I don't need to check endpoints here for inflection points. I do want to say there are inflection points on f when f double prime has a sign change. And I see a sign change at A and a sign change at B, and so I could say there is an inflection point at x equals A on f of x, because to the left of x equals A, f double prime is greater than 0, and to the right of x equals A, f double prime is less than 0. We can also say the same thing about an inflection point at x equals B, because to the left of x equals B, f double prime is less than 0, and to the right of x equals B, f double prime is greater than 0. I will say that this is bulletproof. I will also say most years you can get away with, not all years that I've been reading, but most years you can get away with, there are inflection points at x equals A and x equals B on f of x, because there are sign changes at x equals A and x equals B on f double prime. Remember, the AP reader is not allowed to read sign charts, and so we need to explain to the AP reader what it is that is telling us about the existence of the inflection point, rather than just, oh, they'll see this sign chart too and know like we know. Okay, so that's what I get from my second derivative test, but wait, I get more, because if I had this f double prime sign chart with a plus, a, b, minus, plus, I could say that f is concave up on negative infinity to a, union b to infinity, because f double prime is greater than 0 on those intervals. I could also say f is concave down on a to b, because f double prime is less than 0 on those intervals. Okay, that's good. Notice I'm not including a and b because those are inflection points where f double prime is 0, not positive or negative. But we could also change this, right? And we could talk not about f, but we could talk about f prime. F prime is increasing on those intervals because f double prime is positive, right? If f prime is increasing, that means f prime has positive slopes. The slopes of f prime are called f double prime. F double prime would be positive, f prime must be increasing. And likewise, f prime is decreasing on these intervals because f double prime is less than 0. So we can say that. And there's our first second derivative test. But remember, we had a second derivative test, right? And the second derivative test said if f prime of a was equal to 0 and f double prime at a was greater than 0, we'd be looking at a situation like this. Here's x equals a. We have a 0 slope at a. We have f double prime at a being positive, so we know that f is concave up with a 0 slope, and what we see on this then is a minimum. And so we can say there is a min at x equals a on f of x because of this. This statement is our second derivative test. And what if f prime of a were equal to 0, but this time f double prime was less than 0 at a? Well, now we'd be looking at a situation like this. We have our 0 slope at x equals a, and we can see f double prime is less than 0. F double prime less than 0 means f is concave down. And so I see a max here. There is a max at x equals a on f of x because f prime of a equals 0 and f double prime of a is less than 0. I don't generally use the second derivative test except in cases where I had to do some implicit differentiation. When my derivative has x's and y's in it, I have difficulty checking on either side of a critical point to find positive or negativeness. And therefore, with the second derivative test, I can just find the derivative, the value of the second derivative, see if that value is positive or negative, and that will tell me whether or not my original y equals was going to be, my original function was going to be concave up or concave down, something that had a min or a max at that point. Okay, what else are we asked about here? That was number 4. 5, let's be clear, when f is increasing, what does that mean for f double prime and f? Well, we talked about that. We said that if f prime is increasing, then f double prime is greater than 0 because f double prime is the slopes of f prime. If f prime is going uphill, f prime must have positive slopes. Therefore, the slopes of f prime, called f double prime, must be greater than 0. And whenever f double prime is greater than 0, we know that f is concave up. When f prime is positive, 6, f prime is greater than 0. What does that mean for f? Well, if f prime is positive, that means the slopes of f are positive, and this means that, therefore, f is increasing. Does it mean anything for f double prime? Nope, I don't know anything about f double prime just because f is increasing. Here, f is increasing, f is increasing, f is increasing. F double prime is negative, f double prime is positive, f double prime is 0. I can't say anything about f double prime just because I know f prime is greater than 0. Okay, last thing, for each quadrant, tell what f, f prime, and f double prime are doing. Okay. So in first quadrant, I see, oh, and remember this is the x-axis, this is the y-axis. So yeah, I've got positive y values here, so f is greater than 0. I have a decreasing function here, so f prime is less than 0. And I have concave down here, so f double prime is less than 0. Over here in second quadrant, I see my y values are still greater than 0, so f is still greater than 0. But I also see that my function goes from this low point to this high point, so f prime is greater than 0. But my function is still concave down over here, and so f double prime is less than 0. In third quadrant, the y values are now negative, so f is less than 0. My function is decreasing, so f prime is less than 0. But I'm concave up, and so f double prime must be greater than 0. And over here in fourth quadrant, I have negative y values. I have an increasing curve, f prime is greater than 0, and I have concave up, so f double prime is greater than 0. I hope this was a nice, solid, quick review of some of the basics, and I look forward to seeing you in the next video.